Hello everybody. In this video we will go over 4 ideas and we will show these ideas using TensorFlow Playground. Let's go over the ideas. The first one is a single layer perceptron can solve linear problems only. We will see how it cannot solve nonlinear problems. Next we will see how feature engineering was traditionally used to solve nonlinear problems. However, this is the non-deep learning way of doing things, and currently it is sort of out of fashion. Next, we will see how a multilayer perceptron with linear activation is useless. It cannot learn nonlinear problems. It is the same as a single layer perceptron. And finally, we will see how a multi-layer perceptron with nonlinear activation solves a lot of problems, and it can pretty much learn any general function or mapping.
Now let's learn these ideas using TensorFlow Playground. I love this tool. It is at playground.tensorflow.org and it allows you to learn various things with multilayer perceptron. Now let's go over the interface. First of all, we have the option to choose the data from here, and we have currently chosen a data set that is linearly separable. So here you can see the data. It consists of two axes, x1 and x2, and the orange and blue colors represent different classes. They are saying that the orange one belongs to the orange class, all the blue dots belong to the blue dots. They are not part of the data set. The color is not part of the data set. The data set only consists of x1 and x2. So the location of these points is the data. Next, we are also showing here a separator. So you can see this line that separates the two classes. Right now, this is at an arbitrary location because we have not trained the perceptron. The architecture we are using right now, it is a simple perceptron. It takes the two input and it outputs. And the activation we have chosen is a linear activation, and we are solving a classification problem. Now let's try to solve this problem and see whether the perceptron is able to solve this problem. And when I say solve this problem, on this side of the line, we should have orange, and on that side of the line, we should have blue. Let's get started. So here, it beautifully separated the two classes. It's drawing a line that is orange on this side, which says that any points on this side belong to the orange class, and any point on that side belong to the blue class. So it did a very good job. However, a single layer perceptron can only divide the space using a line. And if it is a three-dimensional space, it can use a plane. If it is a 4 or higher dimensional space, then it will use a hyperplane. So, but the limitation is that it can use only linear combination of these inputs. Therefore, it will be a linear separator. If the data is not linearly distributed, let's pick another data. Stop the simulation and pick this data. Now, this data is not linearly distributed. You can see that there is no line you can draw to separate the two classes. But just for fun, let's try it. It came up with some line which actually does not separate the two classes. So it's not doing a very good job. What used to be done before deep learning was popular is called feature engineering. So instead of using x1 and x2 as input, you create a feature vector that consists of nonlinear transformations of x1 and x2. So here we can actually use x1 squared and x2 squared. And you can see that this has a very good chance of making the two classes separate because we have these squared terms and these elements would have a different squared term than these. These are closer to the origin and therefore they would have separate squared terms. But let's just try to use this and see how it works. Let me reset and just start. Yeah, so it looks beautiful. So you can see that it separated the space into two classes, and the blue one is a circle. That's great. Now, the problem with this approach is that the architecture or the features that we chose, they depend on the data. We chose x1 squared plus x2 squared because the data was circularly distributed. Now, if you change the shape of the data, suppose we actually had this data, then let's try to learn. It may not do a very good job. So you can see that it actually did not do a good job. Let's reset this and add another feature. So we added another feature, we reset the simulation, and we start again. Beautiful. This actually separates the two classes. However, look at the effort we went through. We actually had to have an intuition what kind of features are going to be useful. Now you may ask that why did I choose x1, x2 and not x1 squared, x2? And that's a very valid question. This feature engineering is very difficult. And in 2D, we can actually see how the data is distributed. But in real world, the data is multidimensional and there is no way to easily visualize the data. So coming up with these features, x1 squared, x2 squared, x1, x2, etc., is very, very difficult. And that's why feature engineering is out of fashion. People don't like doing it because we have the new way of doing it, which is the deep learning way. So let's turn off these features. The new way of doing it using deep learning, where we add hidden layers to the network. And you don't need to understand how these hidden layers work. We will come to that in some follow-up videos, but just understand that we will just add one hidden layer and more neurons to this. With this hidden layer, the input gets transformed and it gets manipulated in this hidden layer, and then we try to learn the output using one layer of abstraction. We are still keeping the activation function linear, and let's see what happens when we try to learn this. It doesn't work. It doesn't work because the activation is linear. And that is one point I want to make, that it is the nonlinearity which allows us to learn any function. If we have hidden layer activated using a linear activation, then it is as good or as bad as using just the original features themselves and the original perceptron. So hidden layer with linear activation does not add any learning capability, because again, a linear combination and another linear combination, they add up or they multiply together to form another linear combination. So we don't actually get any benefit. How do we solve this? The answer to it is using nonlinearity. So we added a sigmoid, and let's try to see whether it learns. It learns. It did a very good job. It separated the two classes. For fun, let's also use ReLU. And if you notice, ReLU did converge much faster than sigmoid. Let's reset this again and start. So see how fast ReLU converged. That is a benefit of using ReLU activation, but it also separated the two classes perfectly. But here's the kicker. Suppose we go back to the original function and we simply run the simulation. Notice that we did not do anything to the input. We have this constant architecture we came up with, and we are going to use this architecture to solve a different problem. And it did solve. The same architecture solved a different problem. We did not go and do this feature engineering thing. There is no guesswork involved once we have a good architecture for solving this kind of problems. So that was the huge benefit of using deep learning. We got rid of feature engineering. The features are learned implicitly in the network. So those were the 4 things we learned. Just to recap, first, we learned that a single layer perceptron can solve linear problems. Second, we learned that we can do feature engineering and solve nonlinear problems even with a single layer perceptron, but that's not desirable because when the data changes, our feature vectors need to be rethought and re-engineered. We don't want that. Third, we learned that a multi-layer perceptron with linear activation is just like a single layer perceptron. It cannot solve nonlinear problems. And finally, we learned that a multi-layer perceptron using nonlinear activation can actually solve a wide variety of problems. It can pretty much learn arbitrary mapping. And finally, we also saw that ReLU tends to converge much faster than sigmoid. So that is it for this video. Thank you.